Hello everyone, welcome to Reactify Labs. Today we will talk about a very interesting topic called Merkle Trees. So let's start with the technical definition and everything. And once there is some clarity, then I'll go and explain about its use in daily life and how it works also. Okay. Just before that, um, for clear understanding or so that you have some idea of where in daily life it is used, just for a quick introduction, let me tell you, when you do uh, git diff, in that Merkle tree is used. So let's say you have a very big project, right, and you make some changes to it. Let's say this file was changed, then how does git know what file was changed, or and how does it make sure that it merges at the right place? For that, Merkle tree is used. Okay, now let's start. So a Merkle tree is a hierarchical data structure. It's a hierarchical data structure where each leaf node represents the hash of a data block. Where each leaf node represents the hash of a data block. Okay. So in version control systems, Merkle trees are instrumental for efficient diff calculation and version tracking. So in version control systems, Merkle trees are instrumental for efficient diff calculation. For efficient diff calculation and version tracking. Okay. So what's the basic structure of the Merkle trees? It's just like any other tree. Any other tree, not the binary tree. Okay. So there will be nodes, and there will be leaf nodes, and there will be non-leaf nodes. So that's it. Okay. As you can see, it's not necessary to have only two nodes. It can have more than two also. Okay. And it can be of different heights also. So that's it. So the basic structure says it has nodes. Merkle trees consist of nodes representing the hashed content blocks. Okay, I'll talk about that later. Leaf nodes. Each leaf node corresponds to the hash of an individual file or content block, and then there are non-leaf nodes. Non-leaf nodes store the hash values of their child nodes, forming a hierarchical structure. Okay, so basically, let's say if there is a folder, it's src, it has Java, it has main.java. Okay, so this is a directory, this is a directory, this is the file. So the tree structure for this would be, so this will be the hash of this file. This level will contain the hash of its children. Like it has only one child right now. Let's say if it had multiple files and multiple nodes, and the hash of all these nodes will be stored at this, and the hash of all these children will be stored at this. Okay, so each node stores the hash of its children. Okay, and what happens, how does it detect a change? If any node changes, it means this hash will change. If this hash changes, it means the hash of this will change because the child's hash changed, and thus this hash will be changed. So recursively it will propagate to the top. Okay, we will talk about it in more detail. I did it just for giving you basic idea. Now let's talk about constructing a Merkle tree in version control. Constructing a Merkle tree in version control. So first one is, step one is initial content. begin with the initial content of the files in the repo. Okay, so the files will be there as it is. Next is hashing. Then the hashing will happen. Hashing of leaf nodes. So we compute the cryptographic hash for each file, creating the leaf nodes. Then there will be pairwise hashing. So pair adjacent leaf nodes and hash them together to create higher level nodes. Okay, and then repeat the process. So basically what we did was, we took a file, okay, we hashed it, then another hash, so different files hashed. Okay, now let's say if we have these many files, these got hashed. Now we do pairwise hashing. So for these two, something hash will be there. Again for these two, some other hash will be there. For then these two, some other hash will be there. For these two, some other hash will be there, and for these two, some other hash will be there. Okay, so continue the process until a single root hash represents the entire component. So now we have a single root hash. Okay, so let's say this file changed. Then if this file changed, it means this will change. If this file changed, it means this will change, 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 right? If this file changed, then this changed and this changed. So this is how it works. Okay, so this is how the tree is constructed. Now that you have some idea about it, let's talk about the properties and advantages in version control of Merkle tree. Properties and advantages in version control. So first one is efficient calculation of differences. Efficient calculation of differences. Merkle trees enable version control systems to efficiently calculate differences between file versions by comparing the hashes of specific nodes. Okay. Next is fast version retrieval. Retrieving specific versions is fast, as version control systems can navigate the tree to locate the required version based on the hash comparisons. And tamper detection. Any change in a file results in a different hash, allowing for quick detection of modifications and ensuring data integrity. Okay, so why I am saying this? So let's say you might have noticed that if there is a file and you changed something in it, then in Git you would have seen that the file turns green or some other color, indicating that this file has changed and now it has to be added and committed actually, right? But if you just press Ctrl Z there, or not Ctrl Z, just delete, if you remember what you added, if you just delete it, it changes its color back, right? Indicating that there is no change. Why? Because then it knows that, okay, whatever the previous hash was, it was changed, but when it was changed again, it means this hash became equal to this hash. So it means there is no change, so no commit necessary. So that's what this tamper detection is. Okay. Great. Now let's see use cases in version control systems. So there are different version control systems. The most popular one being Git. So one is Git. Git is a distributed version control system which utilizes Merkle trees to represent changes between commits efficiently. Second one is Perforce. Perforce is a centralized version control system which employs Merkle trees for diff calculation, aiding in version tracking. So both these version control systems use Merkle trees. Okay. Great. Now let's talk about the structure ones. So basically, let's say there are nodes like this: TA, TB, TC, TD, TE, TF, TG, TH. Okay, so these are the files. So this TA is hashed to HA, this TB is hashed to HB, similarly HC, HD, HE, HF, HG and HH. Okay, all these files are hashed. Now, as we have talked about this, two files will be hashed together. So let's say these two files got hashed, means hashes of these two files are hashed. Okay, HAB, then HCD, then HEF, HGH. Now these two will be hashed, HABCD, then HEFGH, and in the end we will get a single root ABCDEFGH. Okay, so this is how hashes are stored. So let's say there is some change to this TC. So this change will change this, which in turn will change this, which will change this, and this will change this. Okay, why? Because then it will have to HD, sorry, this is D. So TD changes, then HD will change because the hash of this file will change. So if HD changes, it means now the hash of these two, combined hash of these two, will be different from what it was earlier. So this changes, similarly this changes, and the root changes. Okay, great. Now let's see how we are calculating differences with Merkle trees. Calculating differences with Merkle trees. First one is selective comparison. Merkle trees enable selective comparison by focusing on the hashes of nodes that have changed between versions. When a file or chunk changes, only the affected nodes need to be compared, optimizing the diff calculation process. So that's why it's called selective comparison. We don't do all the comparisons, right? We don't have to calculate all the 100 files, compare all the 100 files. We do the selective comparison only by checking which hash changed, and only the hash changed. For that, we do the comparison. Okay. Next is recursive hash comparison. Recursive hash comparison. So the system employs a recursive approach to hash comparison, starting from the root and moving down to the leaf nodes. Changes are identified by comparing the cryptographic hashes of nodes, allowing for precise detection of modification in files or chunks. So as we have seen here, this was recursive, right? So it first changed here, then here, then here, then here, then here. But here what I said, starts from root. Yes, it will see that, okay, obviously the change will propagate like this, but then it will check, okay, has the root changed? Yes. If the root has changed, so let's say the root has not changed, then what happens? If the root has not changed, it means there is no change in the file. So that's what. If we start comparing from the leaf node, okay, then what happens is we need to compare all the leaf nodes, then next node, then next, then next. So we can start or stop like this. Let's say we have 100 nodes here, 100 nodes or 100 files. So we have to compare all the 100 files to know if there is a change or not. And let's say we find, let's say this file has changed. Then we will go and check, okay, if there is any other file has changed. And accordingly, we have to go up the root. So we have to do many comparisons. But if we start from root and if there is no change, the root will never change, right? If there is a change in any of these files, the root will eventually change because the change will be propagated. But if the root has not changed, it means nothing has changed. So which makes the comparison process very efficient. That's why we start from root. Obviously, don't get confused it with like when we make any change to the file. If we make any change to the file, it will change the hash by going up. First, it will change this hash, then hash, then hash, then hash. Okay. Once the hash has changed and we try to calculate if there is any diff, then that finding if the diff is there or not, that will start from root. Okay. The hash will go bottom up, but these comparison, recursive hash comparison will start from root. And let's say if there is a change in root, then we know that, okay, root has changed. Now we need to check which of the two children of root has changed. Okay. Or if both has changed. So let's say we know that, okay, this has changed. So we have to only go this route. Then this entire route we don't need to traverse. Okay. So which will again save us a lot of time, which makes it efficient. Then this has changed. Then we'll go to this children. Which one changed? So this one changed. Then we see, okay, this one changed. Then this one changed. So that's how we do the recursive hash comparison, starting from top to down. Okay. Next, let's talk about maintaining versions with Merkle trees. How do we maintain versions? maintaining versions with Merkle trees. Okay. First one is committing changes. When changes occur, a new Merkle tree is constructed to represent the modified content, preserving the state of the repository at that point in time. This process involves creating new nodes for changed files or chunks and updating parent nodes along the path to the root, which I told you before. It starts from the file and then goes up. Okay. Next is commit hash. The commit hash serves as a unique identifier for the version, encapsulating the state of the entire repository at the time of the commit. It is calculated based on the root hash of the newly constructed Merkle tree. Okay. So depending on the newly constructed Merkle tree, depending on the commit hash, a newly constructed Merkle tree will be formed. Okay. Next is historical versions. Historical versions. So each commit in version control corresponds to a specific Merkle tree and consequently a historical version of the repository. Previous Merkle trees and their associated commit hashes allow for easy retrieval and exploration of the repository's history. Okay, if this is not clear, let's understand with this example. Okay, let's go back to the previous example only. It's a good one. Okay, now let's say this is there. So what happens is, once these changes, and you have to commit these changes. So what happens is, when you commit, this entirely is a completely new Merkle tree. Okay. So the earlier one, the previous Merkle tree, which had not changed, let's say it was version 1, and when it has changed after commit, so when you commit, it forms a completely new Merkle tree, which has different hash than this. Okay, after this td changed. So this Merkle tree, let's say this is version 2. Now if we find out there is some issue with version 2 and we have to roll back to version 1, what we do is we just click roll back, and at that time this tree is put in the back and this tree is brought to the front and activated. So now we have again this Merkle tree, this older Merkle tree, which corresponds to version 1. Okay. So this is what the historical version is, and this is how the versions is maintained with Merkle tree. You might be wondering, if you would have ever wondered about this, thinking how Git calculates versions, how Git stores, it has hundreds of versions, how Git makes sure that each version is stored safely. So this is how it does it. Merkle trees. Just to reiterate it again, one version you commit first, version 1 is created. Then you make some changes with any file, even if a dot changes, it creates a completely new Merkle tree, and that's a different version, then different version, then different version. That's why you get the commit history, you get an option to roll back your commit. You can go back to previous commit, let's say version 1, version 2, you have 300 versions. If you now need to go back to, let's say, version 150, you can easily go and switch to version 150. And when you click on version 150, what happens is Git finds the Merkle tree corresponding to version 150 and activates it. And that Merkle tree becomes the viewing point, which is now available for everyone to see, because that is the stable version. Okay. So this is how the versions are maintained in Merkle trees. And I told you how versions are navigated also. Let's talk about theory also. Navigating versions. Navigating versions in version control. So version navigation. The process of navigating back to a previous version involves leveraging commit hashes associated with specific commits. User can specify a commit hash to retrieve the Merkle tree. As I told you, the previous Merkle tree is retrieved, and consequently the file or directory state at the time of the commit. File or directory state means what was the content of the file at that commit, because everything is stored in the Merkle tree, so it's easier to just pull it back. Next is reconstructing state. By following the hash pointers in the Merkle tree, the system effectively reconstructs the file or directory state at the chosen commit. This ability to reconstruct historical states facilitates tasks such as code review, debugging, or reverting to a known working version. This is also the same thing which I explained to you above. It can easily reconstruct the previous stable state. So, if it is providing these many good things or these many advantages, then it must come with its own challenges. Okay, challenges and considerations. First point is handling large repositories. Because whenever we talk about distributed systems, we are talking about large repositories, very heavy systems, a large, very big code base, right? So, handling large repositories. In large repositories, Merkle trees may become deep. The trees will become very deep, potentially impacting performance during diff calculations. Yes, it is not saying that it will be not be able to do it. Performance will be impacted because if your tree is very deep, then the hashes need to propagate, right? First, the hash calculation will be difficult, and it has to propagate up to the root level from so many levels. So that's why the performance will be impacted in this, right? Next is optimizing storage. Ongoing efforts are made to optimize Merkle tree structures in version control systems to balance storage efficiency and performance. Okay, so we have to optimize the storage also, because every commit is creating a new Merkle tree, right? So we need to find ways in which we can efficiently store that tree. So there are ongoing research in that field, how to effectively or efficiently store those Merkle trees. Maybe we can encrypt it, or we can what do you say, compress it, and then when we have to go back to it, if we can expand it without any loss of data, then that can be helpful. But I'm not the one to comment on it right now. Okay, so with this one I finished the discussion about Merkle trees. I hope this gives you a good idea about how Git works, and how your commit history is maintained, how you can roll back a commit, how you can go back to a previous version. Um Next time when you are going to use a Git, you will find how efficiently it implements Merkle trees. You will try to notice how everything that I discussed in this video are being implemented there, and how it helps you make your daily life easier. Okay, so that's it. Thank you for watching. Please remember to like, share, and subscribe. I will see you in the next one.